sun is an enigma. For 70 years, we have believed its core to be a thermonuclear furnace. Yet all our attempts to reproduce the hypothesized fusion have failed. With new technology, we now see the sun in spectacular detail, and what we are seeing is not what we expected. Charged particles defy gravity, exploding from the sun's surface at millions of miles per hour, and then continuing to accelerate out past the inner planets. The sun's temperature increases by millions of degrees as we move away from its surface. Polar jets erupt along magnetic field lines. This activity above the sun's surface requires something beyond a thermonuclear core. But it is exactly what is to be expected from an external electric field acting on the sun. What will happen to the space sciences if we are able to reproduce the features of the sun electrically in a laboratory? The Thunderbolts project extends you an invitation to find out.
If we look at the history of science, we find that science began with the ancient Greeks in what was called the axiomatic approach to natural philosophy. Many of us have experienced this when we took geometry in high school. We learned how to do a proof, where we started with various axioms or postulates, we applied logic, and we derived or proved a theorem. And this theorem is the equivalent of a theory in regular science. And so that was what the ancient Greeks did, and they made plenty of progress in geometry and other areas of mathematics, but they didn't make any progress in physics and the regular science that we deal with today. Many years later, Newton came along and introduced a way to make progress. What he said is all the universe is controlled by forces, and we need to study those forces and to find the unique forces in nature and to record those forces in terms of formulas and equations so that we can describe the forces very carefully and to high precision and determine the minimum number of forces in nature. He developed the force of inertia, F equals ma, and he also did the force of gravity, F equals the gravitational universal constant g times m1, m2 over r squared. These two forces he was able to use as axioms. He took the empirical force law as an axiom, applied the axiomatic method, and developed or derived the theory of mechanics. And this was very successful, and Newton was declared one of the greatest scientists of all time for the work he did. But it was not perfect. When he was interviewed by natural philosophers and they asked him the question, "What is mass?" He said, "Well, mass is a property of matter, and if you cut a piece of matter in half, you have half as much mass." But they asked, is it electric property, is it a magnetic property, or some other type of property? And Newton said, "I do not know." They then asked Newton, well, for gravity, what is the cause of gravity? What makes bodies attract one another? And Newton said, "I do not know." And then a third question they ask is, well, how is the force of gravity conveyed from the earth to the sun or the earth to the moon? And Newton at first thought he could explain it in terms of an ether, but by the end of his life he realized he couldn't, and he had to say, "I do not know." But then he went on to say, "But we have still made great progress. We have been able to write down equations that describe all kinds of phenomena. And even though we don't know the definition of mass, and we don't know the cause of gravity, and we don't know how the force of gravity is conveyed from one body to another, we can still make all kinds of calculations and explain many things. And the world agreed with him. Later, another man came along named Maxwell. And in the field of electricity and magnetism, the scientists had developed 6 empirical laws in the laboratory. Along came Maxwell, and Maxwell took 4 of the experimental laws of electrodynamics and combined them to make his Maxwell equations. And with this, he was able to describe light as a wave. He was able to create the foundation for optics from electromagnetism, and he was able to combine the electric force law and the magnetic force law into a single force law, the electrodynamic force law. This was great progress. But along came some natural philosophers to talk to Maxwell, and they asked Maxwell, what is a charge? Maxwell says, I don't know, and I've approximated it as a point, because I don't know what a charge is. And they asked him, well, what conveys the electric force between one charge and another? Because you have action at a distance force here. And Maxwell said, perhaps it's an ether, but I don't know. And then they asked him other questions that dealt with natural philosophy, and Maxwell came back basically with the same answer that Newton did. Despite what we don't know, we have gained so much knowledge and learned so much, and we can write down equations that describe these things, that we have made great progress in science. At this point, we were very close to perfecting the union of the axiomatic approach and the empirical scientific approach. But at this time, new experiments began to be performed, the Michelson-Morley experiment, the photoelectric effect. And as a result of these experiments, which could not be explained adequately by the Maxwell's theory, new theories were invented, such as special relativity theory, quantum mechanics, and general relativity theory, to explain these phenomena. But these theories branched out in a very different direction from previous theories. They were not based on a force. There was no force associated with special relativity, no unique fundamental force. There was no unique fundamental force associated with quantum mechanics. And so they depended on entirely different kinds of ideas. And they took science into a new direction. But this direction has reached the point where there's no longer any progress being made. The progress that needs to be made is the quantization of gravity, the removal of black holes and the infinities associated with that, the removal of infinities from quantum mechanics and the process of renormalization, and many other philosophical problems that these theories have run into. At this conference, we are introducing the solution to this problem that has plagued modern science for 150 years. The solution is to perfect the union of the axiomatic and the empirical scientific method by including in electrodynamics all 6 of the empirical fundamental laws of electrodynamics in our axiomatic approach. Instead of taking 4, like Maxwell did, we take all 6. We do not use the point-particle approximation. We do not assume that all interactions in electrodynamics are linear, but we allow nonlinear. And we conserve energy, and we satisfy Newton's third law, the force of action equals force of reaction. It turns out in Maxwell's equations, because he did not include Lenz's law, Maxwell's equations did not conserve magnetic energy, and Maxwell's equations did not satisfy Newton's third law for magnetic interactions. Lenz's law says that if you take a magnet and push it into a coil, that an electric current is generated in the coil that pushes back on the magnet and opposes it and causes conservation of energy and satisfies Newton's third law. This was missing from Maxwell's approach. So we put that in. We used all 6 of these empirical laws as axioms in our electrodynamics, and we derived a new force, electrodynamic force, and lo and behold, we discovered that the features in electrodynamics that special relativity theory was invented to explain, including factors of square root of 1 minus v squared over c squared and such things, that all of those are now in electrodynamics entirely by itself with no relativity theory at all.